Hey everyone, it's Mr. Anderson again, coming to you with section 4.1.1 from our Common Core Algebra CPM ebook and video lesson. We are again today going to focus on, as we did yesterday, solving problems from situations having to write equations. And as I mentioned in our last video, this is sometimes a very, very difficult skill for students. And one of the ways we master this skill, or even just improve if we don't master it, is to practice it. I'll talk with you today about some different situations as well as strategies that you can use to improve, grow, increase your skills and abilities. And as I mentioned, this is a second day of section 4.1.1. So we'll start with exactly what you see here, problem 4-6, and we've got three situations, all of which give us different information that we can probably approach a little bit differently. And our goal is to analyze and break down whether or not we can write these situations into one or two mathematical equations. I'll try to define my variables, the thing that I'm solving for or would solve for, using some let statements. But the problem specifically, 4.6, calls out that I do not need to solve these equations. There is one we're going to solve in a future problem, but we'll get there in a moment. Part A is really probably the most manageable part of this, and it's a nice, easy entry point. I'll read it. You follow along. After the math contest, Basil noticed that there were 4 extra large pizzas that were left untouched. In addition, another 3 slices of pizza were uneaten. There were a total of 51 slices of pizza. How many slices does an extra large pizza have? Well, I highlighted something intentional there. I highlighted an important piece, specifically the thing that we're solving for. It says how many slices. So when I go ahead and do this let statement here, folks, I am going to specifically say let x equal the number of slices in a large pizza. Okay, and that's important. Notice I've got that unit on there. It's the number of slices in a large. It's not a medium. It's not an XL. It's in a large. And they want us to write this. And this is a classic one variable, one equation problem. And this, we have experience with this. You could solve this. I'm not going to solve it, but you could. We got 4 extra large pizzas. And in addition, we've got 3 more. So this right here is the number of pizzas we have. We're going to go ahead and multiply that by our number of slices, because every unit that we have is measured in slices, right? Look at this, 51 slices. I've got another 3 slices. So in order to figure out the number of slices in 4 larges, I'll take 4 and multiply it by x. And then I can go ahead and I can add 3 more slices, right? Because we've got another 3. So we'll add those to our total. Presumably those came from a 5th pizza, or maybe 3 additional pizzas where people only ate part of them. And then we've got a total, and total is that word that means to us as mathematicians equals 51 slices, right? And this is a solvable equation. Okay, you could go ahead and subtract 3 from both sides, divide by 4, and come up with the number of slices that each pie or each large pizza has. Okay. In the next problem, in problem B, we've got a little bit more complex of a setup, and it's going to require a slightly different approach. And I'll try my darndest to break down why I'm doing what I'm doing. But again, you can see that I've got the thing highlighted that I'm going to be looking for, right? Herman and Jaquetta are each saving money to pay for college. Herman currently has $15,000 and is working to save $1,000 per month, right? Herman's a good little saver, right? Jaquetta only has $12,000 but is saving $1,300 per month. In how many months, Jaquetta's the better saver, in how many months will they have the same amount of savings, right? And a lot of different info in this problem. For example, we've got 2 rates here. $1,000 per month, $1,300 per month. That tells me I'm probably going to either want a situation in standard form or two different equations. We're going to go two different equations here because in addition to having two rates, I also have two totals. Okay, so the question is, in how many months will they have the same amount of savings? So that's going to be the start. It's going to be how we're going to approach this. I'm going to say let X equal the number of months they saved. Okay, how many months have been going on since they started saving? So that's what X is going to be. X is going to be the number of months they saved for. All right, save for college for. Okay, and I'm going to go ahead and start by writing an equation just for Herman. Okay, I'm going to write an equation just for Herman. And Herman, I'm told, is he currently has $15,000. And he is saving at a rate of $1,000 a month. So he's adding $1,000 a month to that. Yay, good job, Herman. Okay, and I could let this equal his total. And maybe, because I don't know what that total is going to be, maybe we let this be Y. Cool, right? I could do the exact same thing for Jaquetta, right? J for Jaquetta. P.S. H and J and H are not variables. They are simply just identifiers letting you know who's who there. Jaquetta is saving at a rate of, or I'm sorry, she starts with a beginning amount, a beginning balance of $1,200, 12,000, sorry. Definitely very different than 1,200. And she's saving $1,300 a month. And we'll let this equal her total as well. Okay? And maybe you don't want to use Y there. Obviously, there's a couple different ways that you could do this. You'll see maybe in a moment, because I know what is coming next in the next problem, why I specifically did use Y. But we don't have to solve yet this problem, so I'm just going to leave that alone. Notice I took one more time the rate, multiplied it by the variable, and added that starting value. Okay, but again, different situation. I've got two variables, two equations, because of some of the different given information. All right, last one of these before we talk about solving. George bought excuse me. George bought some CDs at his local store. He paid $15.95 for each CD. That's a rate. That's a rate. They're telling me each one costs $15.95. Nora bought the same number of CDs from the store online. She paid $13.95 for each CD, but had to pay $8 for shipping. In the end, both George and Nora paid the same amount of money for their CDs. How many CDs did George and Nora buy? Well, before I go back and break down every single one of those numbers in that problem, I'm going to remind you that I did highlight exactly what it is I'm going to solve for. How many CDs, right? And notice where that comes in each one of these problems. It comes at the end. It's phrased in the question. So our let statement is going to involve that. Let X equal. And if you don't like X, use a different variable. It doesn't matter. I'm using X because it's very commonplace. Let X equal the number of CDs each purchased. Okay? And what I'll do now is I'll back up and I will try to write an equation for each one of these. Little different, and I'll show you why this one lends itself very, very nicely to using one equation, and then maybe you could go back and rethink B with what I'm going to do with it in just a second. Check it out. I've got the info that George, I'll use G for George. George bought what's it called? $15.95. He bought X number of CDs for $15.95 each one. So $15.95X represents the total that George paid. And then over here, I've got Nora. I've got good old Nora. Now I'm doing this backwards on purpose. Nora paid $13.95 for each CD. So $13.95 times X, right? Because X is the number of CDs she purchased, but she also had to pay $8 for shipping. Now check this out. There is some info here that they give us, and I'm going to use that info to our advantage, and it's how we're going to back up and tackle B in just a second. It says George and Nora spent the exact same amount of money buying their CDs. Well, let's take that and use our frames of reference to say that whenever two things are the exact same, they are equal. And so this is a situation where I could have done this like B, where I set this up and wrote two equations, but I'm going to go ahead and just set these two things equal to each other, because maybe I can get by with just one equation here and do some solving like this. All right? And now I'm not going to solve this problem, but you could, of course, go ahead and do this solving and figure out what X is and figure out the number of CDs that each person bought. All right? Keep this idea in mind, because in number 4-7, we're asked to solve part B from 4-6 above, and I want you to check out the similarities. I wrote two expressions, but in B, I set each one equal to Y, and the point of doing that was to introduce a concept. All right, I'm going to back up to here and I'm going to do some solving, and specifically what I want you to realize, recognize, is that if each one of those things is equal to Y, I can swap some items out. What I can do is, if I know this is Y, I can take the known value of Y and I can plug it in, or I can substitute that in to the alternative equation. And that's kind of a big thing that we're going to develop more thoroughly moving forward. But watch what happens when I rewrite this. I can take two equations and I can consolidate into one equation. So I've got two equations, two variables. I'm going to consolidate into one equation with a single variable. Check this out. 15,000 plus 1,000x equals, right, there's that substitution piece, and instead of writing Y, I'm going to write 12,000 plus, and now I've got to have just a tiny bit more room, whoops, 12,000 plus 1,300x. Now I'm going to go a little quickly, not show all my work mathematically, but I'll subtract 12,000 from both sides, and when I do so, I get 3,000 plus 1,000x equals 1,300x. Now I'll subtract 1,000x from both sides, and when I do that, I get 3,000 equals 300x, and I divide both sides by 300, and I come quickly to the solution that x is 10. And remember, we do want to make sure we answer this, communicate effectively, after 10 months. They have the same amount. Okay, but there you go. A bit of a different strategy, taking two equations, combining or consolidating into one. Obviously, you could have approached B like I approached C and maybe set it up slightly differently, but the goal or the thing that we're going to step forward into is that the number of equations we have, the number of variables that we have is, of course, the number of equations that we're going to need to have if we are going to solve. And as I brought up at the beginning, we are writing for solving purposes. Okay? Just a couple more preview problems here. There are four. I know this looks like a mess, but we're skipping around here. There are four, 4 problems, 14, 16, 18, and 19. Ladies and gentlemen, thanks for watching. Have a great day.